Welcome to HTML5 Application Development with Oracle WebLogic Server. My name is Doug Clarke, and I'll be presenting this material today. And with me is Shaun Smith, who will do the demos to illustrate for you how this functionality can be used. The functionality we'll be talking about is included in WebLogic Server 12.1.2, so it is already commercially available and ready for you to use. Near the end of this session, we'll be highlighting some of our future direction in additional capabilities that you may find of interest, and we are not committing to any specific release timeline for this functionality as per this disclaimer. So just to give some scope on what we're looking at, modern web development has changed dramatically over the past couple of years. We've gone to very rich web-based, content-driven applications, integrating new web technologies, native integrations, Flash, and trying to build out your infrastructure to deal with these has become very costly. We need to get expertise in each one of these areas. Developing the content and the web applications is expensive, and then also testing, supporting, and making these work across all of the current platforms and the future platforms has become a very expensive part of our entire IT infrastructure. HTML5 has come along and it's attempted to address a lot of this cross-platform jungle of complexity. It introduces functionalities dealing with offline, real-time communication, file access, semantic markup of the application, and rich rendering of these applications based on CSS3. It's basically taken a lot of the tricks that web developers have been doing over the years and codifying them into a platform with best practices. The structure of the web pages is now well defined in HTML5 documents, which are combined with JavaScript to manipulate and extend the DOM that is actually represented, and then cascaded style sheets, which lets you easily customize the look and feel for different web applications or even different contexts within a web application. So what happens here is HTML5 really changes the game for how we build these rich web applications. Instead of a very server-side rendering-based engine, we now move the application out to the client. HTML5 has UI interfaces across devices for dealing with a lot of the complexity of the data and communication, and even down to the device and file access that we need to deal with. The application now, instead of being something hosted on a server, is really what is running in the browser. The HTML5 I download combined with my custom JavaScript and third-party JavaScript libraries, my style sheets, and then the server resources that I access from the backend to get the data I need to manipulate become the client-side or the browser resident applications. But this really needs us to change how we construct application. Instead of our servers being where we do the markup and generation of the HTML5 based on its perceived context the client is in, the server really becomes responsible for the resources and the services that I need to access. The client is responsible for the presentation logic, what gets rendered in that browser. JavaScript becomes a huge part of our everyday programming model in these web applications, and the predominant data structure for communicating back and forth to the server has changed to be JSON. These applications can also be now constructed to be very event-driven. So instead of having very non-responsive applications, I can actually deal with many different inputs in the browser and through the devices the browser runs on, and also deal with processing asynchronous events driven to me from the server. The WebLogic architecture for delivering this is presented here. We're primarily looking at Oracle WebLogic within Cloud Application Foundation, and the stack for dealing with HTML5 is presented. We're looking at WebLogic Server in combination with frameworks like ADF, our traffic director for routing, and then within the WebLogic Server we have a couple of very relevant technologies. JAX-RS, through our Jersey implementation, does our REST integration. On data services, we have JMS, JAXB, XML binding, services, custom services we can write in EJBs, and JPA for dealing with backend data source access. Then the data sources we can access: relational, NoSQL, coherence data grids, and adapters to other technologies. All of this can be managed through Oracle's Enterprise Manager over its JMX or REST interfaces. Now, most relevant to this conversation is the client-side technologies. So today we'll be focused on HTML5 based browser clients using your favorite client-side JavaScript functionality and third-party libraries. But this could also be any mobile application, whether native or ADF mobile, or even a Java client such as Java SE or Java FX. All that is required to leverage this functionality is the ability to use RESTful interfaces over HTTP and HTTPS, WebSockets for bidirectional socket-based communication, and server-sent events for receiving server-side to client event notification. The stack we're going to be looking at, this is basically the agenda for the talk as well, is getting from browser to database and back. So the different components of that communication, from the browser side, HTTP access, to the back end of the server side, where I have the binding into Java to translate those HTTP requests. I have my Java logic, I have my Java persistence to get to my backend data store, and then I have whatever sort of database stores my enterprise resources. Now we're going to upgrade the browser here in this stack to be an HTML5 browser, leveraging a lot of the capabilities we've introduced. Our HTTP layer will become REST as the most growing or most popular server-side endpoint technology we're seeing today. And then on the Java binding, we're introducing persistence here to deal with the XML and JSON interpretation or transformation of object requests to the server through XML or JSON. Now, to dig in a little deeper, the HTTP or the REST layer in a Java EE stack is implemented with JAX-RS. Our binding persistence layer within the WebLogic Server is based on TopLink's open source component Eclipse Link, which has Moxie, and that deals with the XML and JSON binding, and we'll spend a lot of time on that today. And then on the back end, to get to our database, whether relational or NoSQL, is Eclipse Link JPA. So what we're looking at here is really the flow of data from the database mapped into the object structure of the Java EE application using Eclipse Link JPA. And then included with custom logic and transformation, we can get this information into XML or JSON documents, which become the JAX-RS resources that the browser is going to deal with. And we ship that across and can consume that within JavaScript within my browser application. So really it's this flow of information from the browser to the database and back again. And we're really focusing today at least on the HTML5 based access to data and how that can be done with our WebLogic server to really optimize these style of application development. So for several years now, we've been discussing the powers and capabilities of Oracle TopLink and the Eclipse Link JPA layer for getting from a Java application back to the database. And what we're going to do today is we're going to set that piece aside and really focus on some of the new capabilities and how I go from that common Java object model out to HTML5 through REST. The first piece of that stack is getting from the Java object model efficiently into an XML and JSON representation, and for that we'll use TopLink's Eclipse Link Moxie component. So XML and JSON binding is a pretty well-known problem. JAXB has been around for years and is now part of Java SE, and it really deals with the XML binding portion of it. It has a programming model as well as an annotation configuration model for defining how a given Java class relates to an XML structure. Eclipse Link fully implements a standard JAXB implementation of the latest specification, but we also go well beyond it to deal with some advanced mapping requirements and even the ability to externalize the mapping information out of annotations into a separate XML document, and now I can deal with one object model having multiple XML representations. So within the Eclipse Link project, we've then extended this to start dealing with JSON. Obviously, as a very popular format for dealing with RESTful web applications, JSON binding became very important to us. So what we've done here is we've taken the JAXB implementation within Eclipse Link and extended it to also support JSON. Now, there is no standard for dealing with JSON binding today. Java EE7 introduced the Java API for JSON binding with JSR 535, but this is really just dealing with parsing in the similar to how JSON-P dealt with XML processing. JSON-P deals with the JSON side of processing, but there is no binding standard in this space. So what we did is we leveraged what we already had in our Eclipse Link JAXB context for dealing with how we map the objects and how the mappings can be represented in annotations or XML, and really just taking this same common infrastructure made it usable. So taking a marshaller or unmarshaller, one of these JAXB objects that does the bulk of the loading and conversion logic, and simply by setting the content type on that marshaller or unmarshaller, I can control whether it goes to XML or JSON. And as you will see, this very easy to use flag setting fits very nicely with JAX-RS and our REST integration. So let's look at a simple customer object here. Over on the far left, we have a customer with a simple set of state ID, first name, last name. It has a relationship to an address and a collection of phone numbers. So with some simple JAXB annotations, I can mark this customer as being a root element, and then I can map how the container relationship to the wrapped element's phone numbers relates. So now in the middle, I can marshal that into JSON, and here you see an array of phone numbers using standard JSON notation. And over on the far right, based on the same object without any additional changes, I can get the XML through the JAXB implementation, where I have my phone numbers element with a collection of phone number types within it. And then all of the other address and first name, ID, last name information is presented in the object as well. So this is your basic building blocks of XML binding with the option of rendering using JSON. Now, we discovered a lot of challenges dealing with JAXB and JPA over the years, and that has evolved into several key features of our XML binding, which we've also been able to leverage implicitly in our JSON. These features, or challenges which resulted in features, include handling bidirectional or cyclic relationships, which are very common in JPA and challenging to render in JAXB, composite keys and embedded key classes, and bytecode weaving. All JPA implementations have introduced performance optimizations to deal with how they interact with the database, and these implementations introduce additional bytecodes into the JPA entity classes. When you then try to use these same entity classes as your JAXB base classes that you're binding to, this additional state and functionality starts leaking into the XML documents that JAXB deals with. So if your JAXB implementation does not implicitly know about JPA, you'll end up with a lot of information in your documents that you were not expecting. So this fidelity between the two has become a key part of our functionality set. So let's look at a very simple object relationship to illustrate the bidirectional relationship challenge. Here I have two JPA entities as indicated by the entity annotation, a customer who has a collection of phone numbers, and the phone number knows about its customer. So this is very typical in object relational mapping because the underlying row of the phone table has a foreign key back to its customer. The customer row itself doesn't know, but using that mapped by information, it hooks up the inverse relationship. So when those rows are read out of the database, it can construct the customer object with the collection of phone numbers and each phone number having a relationship back to its customer owner. Now, when I take the same set of objects and try to map them or bind them into XML, I have a customer with my relationships. And when I marshal that into XML, I get a nice looking document like this, a customer with a set of phone numbers. And in there I have each of the types for phone number with their ID. And this looks as I expected. The problem is when I unmarshal it back, each of the customers gets its contained phone number, but the phone number type inside has no knowledge of its contained parent. And this is just a limitation of how JAXB maps these technologies today. And I can't have this because I'm actually losing information in my object model which my application may require. So what Eclipse Link has done within WebLogic and our TopLink product is extend the XML configuration namespace to include an XML inverse reference annotation. And in there, similar to how the one-to-many map by works, I have a map by to phones, which indicates that when you're unmarshalling this phone object from XML, we know it's contained within its parent customer. So when we populate that phone relationship, we can go through and set the customer relationship within the object model. So here I have my same object structure, I marshal it out, and with that configuration I get the full object model back. Now this may seem trivial, but losing data when you're going out to XML, sending it out to the client, it modifies and sends it back is very problematic. So I have a couple of options. I can use a solution like Eclipse Link with this simple annotation, or I can write custom code to post-process the objects when they return, or I could build a secondary object model just for the purpose of marshaling and then manually deal with how it converts back into my JPA entity model and introduce a bunch of code to do that custom transformation. Really comes down to how much code do I want to write, how many object models do I want to maintain, and this functionality, which seems very simple but could show up all over your object model and introduce a set of very repetitive code that is easy to introduce error into. So with this XML inverse relationship functionality, I can eliminate all those capabilities, use the same common object model both for JPA and for XML access. So the next part of the stack we're going to look at is the REST layer for how we expose our resources to the client over a nice clean REST API. REST, which stands for Representational State Transfer, gives us an addressable set of resources. So you have to look at your object or your application a little differently and look for the resources that you want to expose to the HTML5 developer, come up with a small set of well-defined operations to retrieve and mutate those resources, and communicate statelessly, which gives the back end some nice options for scaling because we don't have to be tightly bound to an individual context on the client. The client, or the browser in this case, is responsible for maintaining its own state and knowing how to properly communicate with the REST API. JAX-RS is the Java API for RESTful services. And it really gives us the programming model within Java EE for implementing these RESTful endpoints. It gives us annotations for extending how a bean can be exposed as these endpoints and for how to process the various HTTP request operations that will come at us. The JAX-RS specification came out in EE6 with JAX-RS 1.0 and has recently been updated to 2.0 with JSR 339. At this point, WebLogic is still an E6 container, so it implements the JAX-RS 1.0, but all the functionality we're talking about in this section will be applicable to both standards. So looking at a simple employee invoice service bean, what we have is a class that has a simple method to go and retrieve or read an invoice. So at this point here, we've just mocked it up. And what I'd like to do is show you how you can transform this into a JAX-RS endpoint. The first thing we do is we make it a stateless EJB. So now we have our invoice bean. It has an injected entity manager, and the invoice read method can do an entity manager find, making a retrieval from the back end to get the invoice object and exposing it out to the client. The conversion to be a JAX-RS bean requires the @path, which here we're going to say we have the additional web context /invoice after our web root, and that makes us available to REST calls. The specific REST call that we're going to access today or expose is the get operation. So we've taken this invoice read and say this method is going to be called when we get a get. That get operation is going to have an ID value at the end of its URI, and we're going to map that into the input parameter through the path param. There are many other ways you can do things with query parameters, matrix parameters, but here we're going to do the very simplest based invoice /ID, take the ID off the end, pass it into this method, and then I can invoke the JPA operation. The next question is, what does the data come back as? So on the same method, I can indicate that this invoice read method can return XML or JSON. Now JAX-RS out of the box gives us the capability to integrate JAXB. So when it sees that it can return application XML, if the user doesn't specify, that will be the default value. And it will take the invoice class and construct a JAXB context based on whatever annotations are available, and do the binding into XML. The JSON representation is not implicitly available. What we've done is through our integration with Eclipse Link Moxie is introduce this capability of leveraging the same JAXB context, taking the media type requested in the HTTP GET request, ensuring that it maps onto the produces options here, pass that into the underlying marshaller, and now I can get XML or JSON retrieved from this object request. The get URI here at the bottom shows that I'm going to this machine import whatever the web context root, and all I need to do to implement this method is add /invoice /for on the end, and now I'm doing a get, which translates into an entity manager find for invoice 4. And that will return to me either the XML or JSON depending on which content type I request in the HTTP header. So looking at this graphically, I now have a JAX-RS with JPA stack. So we put Jersey, our JAX-RS implementation, in front of our custom application component, which leverages JPA to map my entity objects to the database. I have the invoice bean that I've shown you, but I might have numerous other beans to expose different parts of my object model and functionality. So when I get a request in from the client, here's my get, same as we've looked at before with the invoice 4. JAX-RS, the RESTful container, interprets that and realizes that the invoice bean exposes that get method we wrote. And within there, it leverages the injected entity manager from the accounting persistence unit, and I can do my operations on the database through my entity manager JPA get. It returns an object that gets implicitly converted into the right representation based on the request. Now, this is great, and JAX-RS does a fabulous job of handling all the complexity of all the different REST operations, but there are some challenges. For every entity within your JPA persistence unit that you would like to expose persistence capabilities to the client, I probably need to implement a get, put, post, delete per entity within one of those beans. Then, within the scope of the marshaled entity graph, I need to limit what comes back in each resource. I don't want to do a request for one object and retrieve the entire database, so I need to cut the object model off at the proper graph or resource level of my REST API. And this generally results in creating a secondary object model for dealing with REST and JAXB, and I have to manually copy my state out of my JPA entity into these and programmatically handle this entity graph resource structure scoping. And then dealing with some of the challenges we've talked about earlier with JAXB, making sure I don't lose any information going out to the client and back, and how much of the code do I want to code manually for every single one of these transformations. Ideally, I don't want to do any of this. So what we've done in this next stage of this presentation, we're going to talk about a new capability that we've introduced in Toplink called RESTful Data Services. And what it does is it takes the Eclipse Link Moxie component, which does my XML and JSON binding, integrates tightly with JAX-RS, and gives us an easy way to expose persistence as a RESTful API without having to write any code. So this new RESTful Data Services functionality has a couple of key components or features. It automatically provides the REST operations for entities. This is very key. Instead of having to programmatically author a bean for every persistent data type to deal with all of the get, put, post, delete operations, it automatically creates the full REST interface for each one of my entities that I want to expose. Any named queries, complex queries, stored procedure operations that I've configured in my JPA persistence unit are automatically exposed as named query get operations in the REST URI structure. The XML to JSON binding is done for me automatically, looking at the JPA entity mappings and the potential for any JAXB mappings I may have added to my classes. It constructs a JAXB context that can do the XML and JSON binding, leveraging all the JPA fidelity features to make sure we don't lose any state between the two conversions, which could result in data corruption on the back end. And then we also have extended the resource model so that we can break apart JPA entities into individual resources and model relationships or links between them so that we can bring fine-grained data access to your HTML5 client without having to introduce a lot of transformation logic. Now plugging this in is very straightforward. All we have to do is add a web fragment jar into the webinflib of our WAR file. That leverages Java EE6 container support, and it looks at the web fragment XML, extends the web archive to include this additional resource, and then processes the JPA persistence units and makes sure the full REST API is available to the consumer. So now our stack looks a little differently. Instead of having each bean of my own, for the point of accessing persistence operations, the RESTful Data Services layer is introduced between JAX-RS and my custom application, my entity classes, and their persistence unit. So now when I make a request using a very similar URI structure, and we'll talk a little bit about what this URI looks like later, we get a request in for a RESTful resource. Now the RESTful Data Services layer takes all the operations with this persistence root and processes them. So looking for the next level of the URI, I see that I have an accounting persistence unit, and then within there I may be looking for an individual invoice to do a get or find operation, which translates into a JPA call, retrieves the object from the database, brings it back into my POJO object model or entity model, and does the binding into either XML or JSON based on the customer's request, and actually scopes the JPA entity's implicit resource at the right level, breaking apart relationships into links based on my JPA configuration. So we have RESTful data services. We get a full REST API for all the CRUD operations of the objects I want to expose. I get implicit JSON or XML conversion. HTTP has a whole bunch of operations, but we've automated the get, put, post, and delete capabilities. So what you as an application developer can do is now leverage all this implicit persistence operations, which is a key part of most application REST URIs. And the only code you're adding in is exposing any custom logic or functionality. All the mechanical needs of the persistence portion is automated for you. Again, all the named queries are exposed. And then a couple other key points here is Oracle top links, caching, mapping, performance, and scalability features such as our server-side caching are all implicitly available to you when you use this solution. We can integrate coherence as a data grid cache. We can map to complex data structures, PL/SQL stored procedures, XML in the database, spatial types. All of that can be handled just by using TopLink. And then this additional layer gives us the REST interface. The last major bullet on here deals with dynamic persistence. And this is a relatively new feature we've introduced in the last couple of years for certain types of users who are building applications where they don't know the object model when they're constructing it, or the object model extends beyond those capabilities. And we've introduced support for dealing with pure XML-based persistence units with no Java classes, and at runtime we'll construct the necessary Java classes. So what this means to RESTful data services is I can actually build a WAR file with a very simple web XML, persistence XML, and ORM mapping XML file, and deploy that and have a full REST through JPA access to my backend database without packaging, compiling, or maintaining a single Java class. And of course, you can combine this with whatever other logic you want. It's just a nice option for customers who don't need to code those Java classes. So finally, here's an example of what a JSON-based resource might look like. Now, I call this a resource because of how it deals with relationships to other resources. It's not really just a JPA entity anymore. I have my first name, gender, ID, last name, collection of responsibilities, salary, the version of this object for optimistic locking. But the unique piece is when this employee or customer has a link to its address, it's replaced in the resource model of the JSON with a link. So now I get an href to how to get this object's related address. And as you can see in the structure, this is what you would see from RESTful data services. I have the server, its port, employee web.js is the application root. The RESTful data services root is persistence. We're looking at version 1 of the API. The persistence unit we're looking at is employee, and then it has an entity called address with ID 18. So that gives you kind of a look at the whole URI structure for issuing this particular GET. And when we step into the demos, you'll see how this URI structure can be leveraged easily within your client application.
Okay, time for a demo. Let's go over to a web browser and take a look at the REST services that we can access. So I've got a simple REST client here. Actually, it's called the Advanced REST Client. It's a plugin for Chrome. And it lets me make calls and look at the results. So I'm going to go to my application that's deployed into WebLogic here. That's my application root. If I go to persistence v10, which is the version of the API we're looking at, and I look for JSON, if I do a get on that, I'll get back a list of the persistence units, in this case the one persistence unit, that are deployed as part of the application. Now in this case I have one called auction, and I can go and I can fetch that also and get more information. So you see here that using this metadata API, I can go and determine that the auction persistence unit contains three entities: bid, user, and auction. I can go ahead and have a look at, for example, auction, and I'm going to do a get on that. And I get the metadata for auction. So auction has a number of properties, has an ID, has a string description, and there's a number of useful link templates here to let me know how to get or put or post a new one. So over REST, I can create an auction, I can update an auction, etc. There's also a number of interesting queries here. So I can do a query to get all the open auctions or all the auctions available to us using a simple URL. Let's give this a try here. You can see actually we have the JPQL here telling you what this query is going to do. So I take the auction query all and send that, and I get back a list of all the auctions. Now in this case there are 5, as you can see here, and to show you the raw is a bit less interesting, but with it formatted nicely we can see that there are 5 in this list, and there's a number of things here. So I have a wireless router, rack mount system, an Apple II. These are all the auctions that we have in our system. So this is the underlying REST API, and with this API I can go off and build a web application. So here I have a simple JavaScript and I believe jQuery and Twitter Bootstrap based application that's using those REST calls we saw to, for example, get all the auctions, which was used to populate this list of auctions here. And as I select each auction, I can go and fetch the bids for that auction that are available. I can go and do things like create a new bid. So for Cindy here, I can create a new bid on this camera of $220. And Cindy now has the winning bid. That's all great. So it's a very nice simple thing. And if I actually go and open up the web console, we can see here in network, as I switch around, we see things happening. We see the bids for auction number 11. So if we just scroll up here a bit, we can see these bids that we fetched. 220 was the highest one. You can see they're sorted around. And so it's all very straightforward. It's pretty much exactly what we expect given these URLs that we've looked at before. So this is very nice for building applications, very straightforward. I had to do no coding to get these REST services to be made available. I just have my deployed JPA persistence unit into WebLogic, and the RESTful data services are enabled by simply including a web fragment into my application. And that web fragment just has a couple of classes that register services when the application is deployed. So that's all it takes. Now, what gets really interesting is with the RESTful data services, we also have connection with Oracle Data Change Notification, DCN, or QCN, Query Change Notification. This is the old and new names for this service. And with that, Oracle database can actually call back to Java, to the middle tier, through the JWC driver to let us know about changes to data that we're interested in. So what we can do is we can connect up an event listener to the callback we get from QCN, and then connect that up with WebSockets so we can have a connection between the browser to the middle tier, WebLogic, back to the database. So we have a bidirectional relationship where as I make changes to data, for example, making new bids, inserting to the database, and then it's one way. And then on the other way back, if someone were to, for example, modify a bid, or I should say, I guess, create a new bid in the database, then that bid can be picked up, notified into WebLogic, and then we can use WebSocket to push notification out to the client. Now, it just so happens that I have a sample application that I have running here, or can run, called AutoBidder. Very simple application. All it's going to do, using JPA of course, is log in. It's going to find all the auctions. It's going to randomly pick an auction, and then it's going to create a bid. That's of course bigger than the highest bid. And so we're going to let this run by itself, and we'll see what it's going to do. So if I run this application here, and it's going to start doing direct inserts into the database. So we see some selects, insert into bid, insert into bid. So there's a timer here, and you can see there's a bit of a sleep, so it doesn't go crazy on us. If I go back over to the browser, if we're careful, and I think we're going to have a look at this guy here, because I think that we can see a change. So the current bid is $34.95 by Goldie. And if we're lucky, we'll get a change to that bid, that auction. Let's try bidding as somebody else here. Let's put in a $4,000 bid. I put a bid in, and it was outbid. Jill, sorry. Oh, and now Simon has outbid us. So we're seeing these direct database edits, updates to database, picked up and sent out right out to WebLogic. So I have this fully integrated system. What's cool about building these kinds of applications is you can build middle-tier based apps, Java-based apps that are relying on back-end database data, that when that data changes, you can be made aware of the change. And go and so far as using WebSockets, we can push that change all the way out to the browser. So you can imagine I have a series of browsers here. I'm going to try this here. I'm just going to steal the URL, and I'm going to create a new browser here, instance, and open up another instance of the auction application. And we'll have them side by side here. All right. So I'll just get rid of the console here because it's not that exciting. And we'll both look at the rack mount. So I can make changes, of course. I'll work as Goldie over here. $5,000. Place the bid, of course, see it immediately. So we have connectivity through WebSockets between the various browser sessions and WebLogic, and from the database to these various browser sessions. So if I sit here long enough and wait for that random number to roll my lucky number here, and update, there we go, update the rack mount system, we see both browsers are updated with the new bid. So we have a nice full end-to-end connectivity here, both sides, all done with very little effort, because really the only coding I did for this application, on the server side, I defined some persistent entities, just JPA entities mapped to tables, and then associations created with the joins, the one-to-manys and one-to-one type relationships. And that was it for the RESTful services. And then on the client, I'm using JavaScript, and I'm just really interacting with the REST services that are automatically generated for me. And that's it. Thanks very much.
Now, as we wrap up this session, there is one other topic I would like to introduce. Recently, at the Open World and Java 1 conferences in the end of 2013, we introduced Project Avatar. This is a new open source effort driven by Oracle to deal with JavaScript processing on the server, and we've launched 2 projects in support of this, avatar.java.net and avatarjavascript.java.net. Now, these 2 projects are available on the java.net hosting service, and I invite you to look at them to see how server-side JavaScript and some of the application programming models introduced there can help you build innovative modern applications. The Avatar architecture is very similar to what we've been discussing in this session, dealing with REST, WebSocket, and server-sent event out to an HTML5 client. On the server side, we have our Java EE container with all of our standard resources, as well as an Avatar server for processing custom web resources and integrating a scripting container with the subcomponent Java Avatar.js, the separate java.net project, and JDK8's Nashorn project to give us this rich server-side JavaScript processing. Then on the back end, we have our standard data access and change notification, pushing changes back into the server. So this really is just an extension of the programming model we've talked about in this session, but allows you to build server-side components using JavaScript instead of just Java EE as the programming model. In summary, we have WebLogic 12.1.2 introducing a lot of this functionality to try to help developers build these rich, thin server architecture HTML5 clients with WebSockets, server-sent events, and all the RESTful integration points. We've introduced TopLink's RESTful data services in this release, which automates the exposure of your JPA persistence units over REST with a nice resource to JPA entity mapping layer, and all the integration for the XML and JSON binding. And then now we've launched Avatar, which will introduce into that same stack a thin server architecture, server-side JavaScript programming model. Thank you very much for your time, and I hope you found this information informative.